Okay. So not everyone was here 4 years ago when I spoke about this last. So somewhere. So let me see now, but how do I but how do I get to the next page?
Page down, I think, works.
Yeah, but I can't find any page down.
I mean, on your laptop.
Well, it's not on my keyboard, that's for sure.
You got it.
No, that's just all right, well, let's see what I can do. So so let's start with a kind of review of we have an n by n matrix with real coefficients, and the jth column sum is the sum of the coordinates in the jth column, and this is supposed to be, it's supposed to say this is a positive matrix. So all the coordinates are positive, so every column sum is positive. And
Can't you allow some entries to be 0?
no, positive means positive. This is so consider a positive n by n matrix, and I say positive means strictly positive. Every coordinate is greater than 0. The ith row sum is the sum of the coordinates in the ith row, so that has to be a positive number. And the matrix is called, said to be row stochastic if every row sum is 1. And similarly, the jth column sum is the sum of the coordinates in the jth column, and the matrix is column stochastic if every column sum is 1, and the matrix is doubly stochastic if it's both row and column stochastic. So for example, a permutation matrix is doubly stochastic. A circulant matrix is. Other matrices have different shapes, and they can be doubly stochastic. And for various curious reasons, there has been certainly historical interest in doubly stochastic matrices. But a random matrix, a typical matrix, is not doubly stochastic. So here, for example, is a positive 3 by 3 matrix. And one can ask, how can you convert this to a doubly stochastic matrix? So there's one easy solution. Replace this matrix because I don't have page down. Goddamn. So I could replace it by this. So this matrix is not doubly stochastic, and this one is. Of course, somehow in the transformation of A to this thing, we've lost any information about A. So that's not an entirely sympathetic solution. So one might ask, for whatever reason, is there a way to convert a matrix to a doubly stochastic matrix that somehow retains some relevant information about the matrix you start with? Now, there's no obvious way to do that, nor do I have any idea whatsoever what it means to start with the matrix and obtain or construct a doubly stochastic matrix which has some information about the matrix you started with that you want to keep. If you only look at row stochastic or column stochastic matrices, there's a natural algorithm you can choose. So if you have an n by n matrix with positive entries, you can take the diagonal matrix X or X of A, where the entries down the diagonal are the reciprocals of the row sums. So this should be an n here, but 1 over the first row sum, 1 over the row second row sum, and third sum. If you multiply the matrix A on the left by X of A, that simply multiplies the first row by this number, every coordinate in the second row by this number, every coordinate in the last row by this number. And now when you do the row sum, you get the row sum divided by the row sum, which is 1. So this is a way to scale the rows of the matrix to get a matrix which is row stochastic. And you can do the same thing to start with a matrix and column scale it. So if you have your n by n matrix, you can look at all of the column sums, take the reciprocals of those numbers. These are the column sums, and form this diagonal matrix where you have the reciprocal of the column sum down the diagonal. If you multiply your matrix on the right by y, you're multiplying the ith column by 1 over the ith column sum. So the new ith column sum is going to be 1. So this is a way to right scale the matrix to get a column stochastic matrix. So for example, if you start with a matrix 1, 2, 3, 4, and you row scale it, so the first row sum is 3. So in the new matrix, the first row is 1/3, 2/3. The second row sum is 7. So in the new matrix, the coordinates are 3/7 and 4/7. Conversely, if you take this matrix and you column scale it, let's say we take this matrix, so it's row stochastic, but it's not column stochastic. If you want to make it column stochastic, you apply that little trick to the columns. So you take the sum of the columns and divide each column by that sum. So let's see, I have no idea if my arithmetic is correct.
1/3 and 3/7 is 16/21.
Okay, so 1/3 times 16 times 20, then you take the reciprocal, times 21 over 16 is 7 over 16. So if you column scale this matrix, you get this matrix. Now this matrix has columns that sum to 1, but the rows no longer sum to 1. So if you have a matrix, you can make it row stochastic in a natural way, but it's not column stochastic. Or you can make it column stochastic in a natural way, but it's not row stochastic. And what is so what one often does in that situation, and this is done analogously often when you have a function of several variables and you're trying to find a global minimum, you might fix all but one variable and then minimize on the on the remaining variable, and then take the next variable and do the same thing. And you alternately minimize, and you pray that the sequence of things you get will converge to the minimum of the function. So you can do the same thing here. It's sometimes called alternate minimization. You take your positive matrix and you construct inductively a sequence of n by n matrices by alternate operations of row scaling and column scaling. And let me make it what is definitely a true statement. This infinite sequence of matrices might converge to a doubly stochastic matrix. I'm not saying it does, it might. You don't know. I don't know. Moreover, it's possible that there might even exist positive diagonal matrices X and Y, such that when you take A and left multiply by X and right multiply by Y, which means you're scaling the rows by X and you're scaling the columns by Y, you end up with a matrix S of A that is doubly stochastic. All right. In fact, it might even be the case that this sequence of diagonal matrices, two sequences of diagonal matrices that you get by alternately row and column scaling, those sequences of diagonal matrices might even converge to the matrices X and Y that would give you a doubly stochastic matrix. Right? What is definitely true is the following. There's the following uniqueness. So again, we have a fixed n by n matrix with positive coordinates. And suppose there are positive diagonal matrices x, x prime, y, y prime. So x, a, y is doubly stochastic, and x prime, a, y prime is doubly stochastic. If that is the case, then S must equal S prime, and X prime, so then there's some positive number lambda, such X prime is lambda times X and Y prime is lambda inverse times X. So this is a true statement. I'll give a proof of this in a couple of minutes. Okay. So there's a case where we know explicitly what is the doubly stochastic matrix that you get from this process. So suppose we take a 2 by 2 matrix that's positive. There is, let's say, by divine inspiration, I have this matrix X, which is positive diagonal, because A, B, C, and D are positive. And this matrix Y, which is positive diagonal. And if I left multiply A by X and right multiply A by Y, I get a matrix alpha, beta, beta, alpha, where alpha and beta are these numbers. So we get so we know explicitly what is the doubly stochastic matrix that we get by left and right scaling. Okay. For 3 by 3 matrices, no one knows how to write down the doubly stochastic matrix you might get.
You mean there's no general formula? For some special families, we could get explicit formulas.
Yes, but there's no general formula.
Do they always converge?
I said they might. That's part of the history of this that I'm going to talk about.
Oh, okay.
Right. So if you take 1, 2, 3, 4, and you left and right multiply, as I said, this is the limit that you get. If you check the arithmetic, it is doubly stochastic. That's a good thing.
Do we know for a fact that the limiting process will produce this matrix? I mean, we know that multiplying on left and right will produce it. Do we know for a fact that the infinite sequence will converge to this?
Right. So it depends on who is included in that first person plural pronoun we. Okay. I'll explain. That's sort of the point of my talk, as an exercise in the history, philosophy, or sociology of mathematics. Yeah, in this case, it's actually interesting. If you take the matrix 1, 3, 3, 4, the associated doubly stochastic matrix is this. And in this case, you multiply on the left and the right by the same matrix. And that's a general fact about symmetric matrices. If you have a positive symmetric matrix, there's always one matrix X such that XAX is doubly stochastic. And that's true for n by n matrices, not just for 2 by 2 matrices. Okay, now, this all comes from the work originally, well, it's a little bit murky, but a guy named Richard Sinkhorn. Richard Sinkhorn got his PhD in 1962 from the University of Wisconsin. And And he writes, this is not in his thesis, which I'm still trying to get a copy of, but the iterative process of alternately normalizing the rows and columns of a strictly positive n by n matrix. So this is what Russell was just asking, is convergent to a strictly positive doubly stochastic matrix. It is not the intent of this paper to obtain properties of this estimate, but only to examine the mechanics of the iteration itself, right? The properties of the estimate, this is something, I don't know who might have looked into this or considered this, cared about this, but this is in some sense just looking at the operation of the algorithm. So Sinkhorn wrote his thesis in 62, submitted his first paper for publication in 62, and it was published in 1964. And in that paper, he states the following two theorems. First, to a given n by n matrix, there corresponds exactly one doubly stochastic matrix, he's calling it T sub A, which can be expressed in the form D1A, D2, where D1 and D2 are diagonal matrices with positive diagonals. The diagonal matrices are unique up to a scalar factor. So this is in fact a true theorem, but as I read Sinkhorn's paper, he doesn't prove the theorem. He proves the uniqueness, and he proves something else that I will mention, but he doesn't prove the theorem. And the second theorem he states is that the iterative process of alternately normalizing the rows and columns of a strictly positive n by n matrix is convergent to a strictly positive doubly stochastic matrix. So this is a theorem that he states, but this he does not prove, all right, in this paper. Okay. Now, this is his thesis. So on two problems concerning doubly stochastic matrices. And I've asked interlibrary loan at CUNY to try to get me a copy. But because it used to be in ancient times, those of us who are ancient will recall, before they had computers, you would send your thesis to someplace in Ann Arbor, Michigan, and they would make like a microfilm of it or something. So it could be retrieved by people who you could maybe buy the microfilm and then put it in your microfilm reader. But in principle, all theses are supposed to be there, but in practice, I know not all of them are. So I'm really curious to look at this thesis, particularly because, so again, in ancient times, before you could post a preprint on archive or on a computer, one way you told the world what you had done before your paper was published, so people would know, or you might have priority if that was of interest to you, is you sent an abstract to the notices of the American Mathematical Society. And they would print abstracts. They would certainly print abstracts of talks that were going to be given at AMS meetings. So Sinkhorn in 1962 posted the following abstract in the notices. And I literally just found this, I mean, in the last week or so. Let me try and get it back. Because there's more information in his abstract than is in any of his papers. And that's why I'm curious to see his thesis, whether what he claims in his abstract is in his thesis. So in the abstract, he says, to any given strictly positive square matrix A, there corresponds a unique doubly stochastic matrix T sub A, which can be expressed as A multiplied on the left and right by diagonal matrices. And then he says, this matrix, the doubly stochastic matrix, can be obtained from A as a limit of the iteration defined by alternately normalizing rows and columns of A. And now he says something which I have not seen in any of his papers, and it's really, I think, quite important to the half dozen people in the world who care about this. That is, of course, an upper limit. It might be much less than that. The rate of convergence is geometric, So there is a number nu between 0 and 1, such that the difference between the doubly stochastic limit and the nth iterate. So you can take this, you can pick your favorite metric, the maximum of the coordinates, for example, is less than c nu to the n. So this is decreasing geometrically as n goes to infinity. And that says exactly that the nth iterate, the sequence of nth iterates converges to T sub A. So if this were true, his theorem would definitely be true, and in a very interesting way. And he says further, the convergence is uniform with respect to A on compact subsets of the positive n by n matrices, which is like the positive orthant in n squared, Rn squared. And so TA is a continuous function of A when A is strictly positive. When A is non-negative but contains 0 entries, certain peculiarities develop. I can explain what they are, but that's not relevant at this point. Okay. So that was the abstract. It's hard for me to get from one page to the next here. Yeah, I just want to point out, he does not prove either of the two theorems he claims in his paper. His paper has some interesting stuff in it, very interesting stuff, but it's not in the paper. But no one seems to have cared or to have noticed. So a few years ago, a guy in Germany named Idle posted on Archive an extremely valuable survey of work that followed from Sinkhorn's theorem. He says the literature is vast. It's a huge literature. It's become particularly important in computer science because Avi Vigderson and his group of people became very interested in this, but from the point of view of computer science. So what Sinkhorn is talking about is exact matrix scaling, giving a matrix A with non-negative entries, or in our case, we're just talking about positive. Find diagonal matrices R and C says that RAC is doubly stochastic. But what Avi says is, for more relevant to us, is its approximate version, which only requires that this matrix B that you get by multiplying A on the right and the left by diagonal matrices is arbitrarily close to a doubly stochastic matrix. This is exactly what Sinkhorn does prove in his original paper. He doesn't prove convergence, but he proves, if you look at the sequence of matrices obtained by the iteration, that their row and column sums converge to 1. But the fact that a sequence of matrices has row and column sums converging to 1 doesn't mean that the sequence of matrices converges. But from Vigderson's point of view, that's exactly what you're interested in computer science. And what he and his a large group of collaborators have studied has to do with the rate of convergence. You want to know whether you can get within epsilon of a doubly stochastic matrix in polynomial time, for example. That's the sort of thing that the computer science people are interested in. But the fact that you do have this approximate convergence, this is exactly what Sinkhorn does prove in his original paper. So let's see. All I'm saying here is you start with the matrix A. By C of A, the matrix you get by column scaling, and by R of A, it's the matrix you get by row scaling. So you generate the sequence of matrices starting with A by alternately column and row scaling. And in the notation here, the X's are the diagonal matrix you get when you row scale, and the YLs are the diagonal matrices you get when you column scale. So if you start with A and you iterate the row and column scaling L times, you get these matrices. Each time you start with A, you're multiplying on the left or the right by another diagonal matrix. And for the unprime matrices, these are column scaled, so the column sums are 1. For the prime matrices, these are row scaled. This should be a prime here. The primes are 1. And if somehow you knew that the diagonal matrices, the product of these diagonal matrices converged, that would give you everything that Sinkhorn claims. But as far as I know, in the 60 years or so that this has been of interest, no one has proved this. So this has to do with matrices. So let me just put in a plug for a very good book by Marcus and Minch, A Survey of Matrix Theory and Matrix Inequalities. It's a cheaped over paperback. And there is, as most of us know in principle, a large theory about matrices, most of which I'm utterly ignorant of. It's old-fashioned matrix theory, and this is a great source for that. And I mentioned just 2 theorems about matrices, which are key in much of the work on the Sinkhorn problem. So, so the first is the Frobenius-Koenig theorem. It says you take an m by n matrix, and you have, suppose it has an S by T submatrix. So a submatrix is a matrix you get from a matrix by choosing S rows and T columns, and you only look at the coordinates that lie on both the S rows that you picked and the T columns that you picked. So that's an S by T submatrix. And your matrix may or may not contain an S by T 0 submatrix. And if it does, you can permute the rows and columns. So they're permutation matrices P and Q, such that PAQ has like the 0 matrix wherever you want to put it, for example, the upper left-hand corner. What is the support of a matrix? So your 2 favorite diagonals in a square matrix are the main diagonal, the 1, 1, 2, 2, and so forth entries, and the anti-main diagonal, which instead of going from the upper left to the lower right, goes from the lower left to the upper right. But in general, a diagonal of a matrix comes from, there are n factorial of them, coming from a permutation. So if you have a permutation sigma, you take in each row the coordinate, in row I, you take the coordinate sigma of I. So you're choosing one element from each row, and these elements all belong to different columns. So so you have a diagonal, and you multiply the entries, and you either get 0 or you get something non-zero. So if a diagonal has a non-zero entry, then that diagonal, right, so you have a diagonal that might have a non-zero entry. But it can be the case that every diagonal in a matrix is 0. That is, you can't find a diagonal which has no non-zero element. And we say that a matrix has support if it has at least one non-zero diagonal. So, and the Frobenius-Koenig theorem says that a matrix has support if and only if it does not contain an S by T 0 submatrix with S plus T equal to N plus 1. So this is actually a lovely theorem. It's very interesting, fun to try to prove it. All right, but that is and I actually wrote down a proof, which I don't want. So let me try to. it truly is impossible to go from slide to slide here. I don't know why. Oops. All right. And then the other fundamental theorem about matrices that one uses is a theorem that was discovered first by Birkhoff. Von Neumann gave a different proof. And for some reason, it's called the Birkhoff-von Neumann theorem, presumably because there are too many theorems that could be called the Birkhoff theorem and too many theorems that could be called the von Neumann theorem. Now, parts of the ergodic theorem could be called the Birkhoff-von Neumann theorem, but what is called the Birkhoff-von Neumann theorem is this theorem about permutation matrices. So permutation matrix is a matrix which has on every row exactly 1, 1, and the others rest 0, and on every column exactly a single 1, and everything else 0. So every permutation matrix is doubly stochastic. It's a straightforward check that if you look at the set of all doubly stochastic matrices, that's a convex set. It's closed under convex combinations. And the Birkhoff-von Neumann theorem says that the set of doubly stochastic matrices is the convex hull of the set of permutation matrices. So if you have any permutation matrix, you can write it as a convex combination of permutation matrices. What does this say about the question of support? Remember, support, a matrix has support if it has at least one non-zero diagonal. We say a matrix has total support if every non-zero coordinate is part of a non-zero diagonal. Now, suppose you have a permutation matrix. So it can have zeros, but take a coordinate which is and a permutation matrix has non-negative coordinates. Take a coordinate which is positive. Well, if the coordinate is positive, fine, but the doubly stochastic matrix is a convex combination of permutation matrices. So there's some permutation matrix which has a 1 in exactly the place where your non-zero coordinate is. But in a permutation matrix, there's exactly one diagonal, non-zero diagonals, the diagonal that has all the 1s in it. So if a permutation matrix has a 1s, if a doubly stochastic matrix has a 1 somewhere, it's part of a non-zero diagonal. So every doubly stochastic matrix automatically has total support, which answers the question whether, if you start with a matrix A, maybe the process of alternate row and column scaling leads to a doubly stochastic matrix. But if your original matrix does not have total support, then your doubly stochastic matrix cannot come from left and right multiplications by fixed diagonal matrices, because that doesn't change the pattern of the matrix. It doesn't change a non-zero coordinate to a 0 coordinate. So if you don't have total support, this alternating scaling process might converge to a doubly stochastic matrix, but it will not come from left and right diagonalizations. All right. So I said that Sinkhorn did not prove his theorem, but the theorem about every positive matrix can be left and right multiplied by diagonal matrices to get a doubly stochastic matrix. So that was proved a few years after Sinkhorn's paper by a guy named Menon, M-E-N-O-N, and he had a beautiful proof, and the proof generalizes a little bit so I just want to show you Menons' proof of this, and the proof uses Brouwer's theorem. Brouwer's theorem says if you have a unit ball in Rn, every continuous function from the ball to itself has a fixed point. So how do we get a continuous function on a ball out of Sinkhorn's problem? So here we fix some notation. So we take Rn, and the non-negative orthant is denoted the way it's shown on the screen. So it's all vectors with non-negative coordinates, and so a vector in the non-negative orthant is a non-negative vector, and non-zero non-negative vector is simply a vector with non-negative coordinates, and not all of them are zero. And a positive vector is a vector all of whose coordinates are positive. Oops. So the one-dimensional sphere in Rn, it should say, is all vectors whose length is 1. And I'm interested in the non-negative part of the sphere. So I want to look at all vectors in Rn of length 1 with non-negative coordinates. And that set is homeomorphic to the n-1 ball. And if I take a vector, any non-zero non-negative vector, and divide by its length, that gives me something in the n-1 sphere in the non-negative orthant. So this function gamma, which takes a vector and divides by its length, I'm calling it gamma. So gamma of z is z over the length of z. And so if this just says if you take the non-negative orthant of the sphere and you project it down into the Rn-1, you get a compact convex set, which is homeomorphic to the closed n-1 dimensional ball. So, okay, so I have to, where are my functions? This is the uniqueness statement. I'm not going to prove it since everything is taking much too long. Okay. One can generalize in a very simple way the idea of doubly stochastic matrices. If you take a positive matrix, A, now this is Sinkhorn, the theorem Sinkhorn stated. If A is n by n and positive, you can left and right multiply and get a doubly stochastic matrix. The somewhat better theorem is the following. If you let R be a positive vector and C be a positive vector, R has m coordinates and C has n coordinates, and you have the condition that the sum of the R's is equal to the sum of the C's, then there exist positive vectors X and Y with associated diagonal matrices D1 and D2, where D1A, D2 is RC doubly stochastic. That means in this matrix, the sum, if you take the sum of the coordinates in the ith row, you get Ri for all I. If you take the sum of the coordinates in the jth column, you get Rj for all j. So that's a baby extension of the notion of being doubly stochastic. So you can go to rectangular matrices and so on. Okay, so for every positive vector C, so we fix C, that's going to be our column sums. We can define a continuous function from the non-negative orthant in Rm to the positive orthant in Rn as follows. So you take a non-negative vector x, and you take the matrix A, and you scale the rows by the matrix X. So XA is this matrix Xi, Aij. And you look at the column sums. So they're positive, because all the numbers we're looking at are positive. But the column sum is not necessarily equal to Cj. So if you let Yj be equal to Cj divided by that column sum, then Y is a positive n-dimensional vector. And the matrix XAY, you've just column scaled the rows. So XAY is C column stochastic. That satisfies this condition. Similarly, if you take a positive vector R and Rm, I can construct a continuous function beta from the non-negative orthant in Rm to the positive vectors in Rm as follows. So I take Y in Rn and I row scale A on the right by Y. So this scaled matrix has these row sums. Again, Y is just an arbitrary matrix. These row sums are not necessarily what we want, that is equal to Ri. So I can define Zi to be Ri over this row sum. That Yj should be in the denominator. And I get a positive vector. And this positive vector has the property that summation Zi, Aij, Yj is equal to Ri. So now I have a continuous function beta from Rn, from the non-negative orthants of Rn to Rm, beta of Y equal to Z. Now, Z is not necessarily a vector of unit length, but if I apply gamma to Z, I get a vector of unit length. So I have a composite function, gamma beta alpha, from the non-zero non-negative vectors in Rm to the unit sphere Sm minus 1, but the non-negative part of it. And that's a continuous function. And I take this function and I restrict it to the unit sphere in that non-negative orthant. So phi is a continuous function from this part of the unit sphere to this part of the unit sphere. Now, the unit sphere is not contractible. There's nothing, I mean, there's a Borsuk-Ulam theorem that has to do with continuous functions on the sphere, but we're not on a sphere. We're on a piece of the sphere. And the piece of the sphere is essentially the same or homeomorphic, if you like, to a solid ball of dimension m-1. And so if I restrict phi to this sphere, the sphere is homeomorphic to the ball, the solid ball. So Brouwer's fixed point theorem says there's an x, which is a fixed point of this function phi. That is, phi of x equals x. Phi of x, that's gamma beta alpha of x. Alpha of x is y. Beta of y is z. And gamma of z is z over the length of z. So the ith coordinate of the vector z is this positive scalar, absolute value of z times x sub I. And we have that the xi, aij, yj, that xay matrix was column stochastic. So this is the column sum, the jth column sum of xay. And if you sum all these column sums, you get this sum, which is the sum of the CJs. And if you do the same thing to the row sums, so first of all, z times the sum of the CJs, that's exactly this, but z times xi is zi. And this, you can interchange the summation, this is the row sums, and each of these row sums is Ri, and the sum of the Ri's was equal to the sum of the CJs. So if this equals this, and this sum of the CJs is positive, you cancel, and you get that z has length 1. That means xi equals zi. So I have for the matrix XAY, the row sums are Ri, the column sums are Cj, and the matrix is row and column stochastic. So that is a perfectly good, lovely, legitimate proof of Sinkhorn's theorem, or at least of the part of Sinkhorn's theorem that says that if A is positive, then they're positive diagonal matrices X and Y, such that XAY is doubly stochastic, or more generally, RC stochastic. This says nothing about the convergence of the convergence process. All right, absolutely nothing. Okay. Now, I'm just going to close with one last thing. No one has ever explained, I've never read anywhere that gives a sufficient reason why, that says what this Sinkhorn limit. So you have your matrix A, and you apply this Sinkhorn process, if you like, and you get a doubly stochastic matrix, S of A. What does S of A tell you? I have absolutely no idea. I mean, you have an algorithm that starts with a matrix and produces a doubly stochastic matrix. This can come up in practice if you have a Markov process, and you have a finite Markov process, finitely many states, and you have some reason to believe that the transition matrix isn't just row stochastic, but it's actually doubly stochastic. Then, and you have some data, right? That is, you've collected some data. So you have some heuristic, you have some numbers about, in a given population, how many in step I end up in stage I end up in stage J. So you have some integer matrix with positive integral entries, and you want to get a doubly stochastic matrix out of that. You somehow want to get some idea of what the actual transition matrix is for your Markov process. So applying Sinkhorn, you start with A and you get your doubly stochastic matrix. But I have no idea why anyone should believe that that doubly stochastic matrix has anything to do with the nature of the world. So I came up once with a different way of creating a doubly stochastic matrix out of a matrix. So suppose you take a n by n matrix A with positive coordinates, and by XA, I mean take A and row scale it. So XA is what you get when you row scale A. That's uniquely defined. Alternatively, you can start with A, and there's a unique diagonal, positive diagonal matrix Y, such that AY is column scaled. Now, in the Sinkhorn algorithm, you apply these X and Y actions one after the other. A, then XA, then XAY, then XAY. You left scale and right scale, left scale and right scale alternately. But how? Why do that? I mean, you can do that, but maybe instead you should just do in one step. Take your matrix A. This is the row scaled version. This is the column scaled version, and take this convex combination of them. So starting with A, you get this matrix. Again, this matrix is most likely neither row stochastic nor column stochastic, but hell, I mean, repeat the process, right? So you start with A and you construct this new matrix. And from this matrix, you apply the same formula and you get a new matrix. So you generate a sequence of matrices depending on lambda. So 4 years ago, there was an infinitely bright kid who was in a one of these undergraduate summer research programs at CUNY, and I was asked to give a talk to the group of students, and one of them was a guy named Alex Cohen, who at the time was maybe he was a freshman at Yale, and now he's a graduate student at MIT, and he proved that for any lambda, so long as 2 by 2 matrices, it doesn't work for. But if you have matrices that are 3 by 3 or bigger, for any lambda, when you iterate this algorithm, this converges to a doubly stochastic matrix, right? That's a fantastic result. And is it the matrix that you get from Sinkhorn's algorithm? No, it's a different doubly stochastic matrix. And does it depend on lambda? Yes. As you vary lambda, you get a whole continuous family. I shouldn't say continuous. You get a whole family of doubly stochastic matrices that depend on lambda. Are these better or worse than Sinkhorn's doubly stochastic limit? I have no idea. I haven't the faintest idea. But Alex Cohen, by the way, is going to be a really great mathematician. And he recently did something. If you look at the Quantum magazine, quantummagazine.org, a couple of months ago, whenever someone does something spectacular in mathematics, they write it up in Quanta. And he and someone else at MIT did something spectacular enough that they wrote a whole article about his preprint there. But this, he was really just out of high school when he did this. And so this algorithm, this procedure, this converges to some doubly stochastic matrix depending on lambda. And what does that tell us? I haven't the faintest idea. Just as I haven't the faintest idea what Sinkhorn's algorithm tells us. It just gives us a doubly stochastic matrix. Well, yay. I mean, all right. I have no idea what it means.
Does there exist a lambda which gives you the Sinkhorn limits?
I'm sorry. What?
Sorry. So H lambda gives you in your algorithm, Alex Cohen's algorithm, gives you a different doubly stochastic matrix. Does there exist a lambda that will give you the Sinkhorn matrix?
I have no idea. I know if you take the simplest choice, lambda equal to a half. So at each stage, instead of like right scaling and left scaling, you take the average of the right, so instead of alternately row and column scaling, at each stage, you take the average of the row scaled and column scaled. That gives you a different matrix. Now, Alex Cohen actually, in a couple of cases, so you can fix one coordinate as a function of lambda. You get some curve. I mean, we got a curve. What curve is it? Who knows? I have absolutely no idea. Yeah, no idea. So anyway, so there's several interesting things for me here. One is this historical point. It's one of the slides that I sort of couldn't get to show up on the screen. After Sinkhorn, actually, it's really interesting. This was this guy's PhD thesis at Wisconsin. And basically, if you go to Math SciNet and you look up his papers, everything he did for the rest of his career was more or less variations and elaborations on this theme. But his original paper, his first paper, which presumably was like directly from his thesis, even though he didn't prove the theorems, everyone believed he did. And doesn't matter because there are a huge list of people refining his stuff or proving other things. And the first sentence of all of their papers is, in 1964, Sinkhorn proved the following theorem. And he did not prove that theorem in 1964. He just did it. Parts of it he did prove later. He had I don't know whether it was a postdoc, a graduate student. There was one of the many mathematicians named Knopp, spelled K-N-O-P-P. I mean, many of us knew Marvin Knopp from who started was a graduate student at Wisconsin. Or we learned complex variables from the Dover paperbacks by Knopp. But there was a third Knopp who was a co-author with Sinkhorn, where they did give a proof of some of his, actual proof of some of his theorems. But everyone cites that 1964 paper as correct. And I actually wrote to this guy in Germany, Idel, I-D-E-L, who wrote the survey on Sinkhorn. And I said, paper, he doesn't prove the theorem. And what Idel wrote back was something like, yeah, almost all of the original papers on this subject had mistakes or were incomplete. And, but no one cared. All right. Let me just, or no one realized it, because, people can be sloppy. But I just find it interesting, people who aren't mathematicians still believe that mathematicians really prove theorems. And they think it's like high school geometry. You can, you write down 10 lines and, A implies B implies C implies what you want to prove, but it's just not true. Also, David, is there a non-standard way to prove the convergence of this sequence of iterations? My standard question, if I see you, is, but can you do this with non-standard methods? So
I can't do it right now. Usually you don't get something for nothing, right? Which means that if there is, it's really just probably a simplification of what you get with the standard one. But I don't know. Sure, one can look and see. I'm curious. So his advisor was Creighton Buck, who was an applied mathematician. He was Sinkhorn's PhD advisor. Buck did like approximation theory and
my course in advanced calculus was a book used a textbook by Creighton Buck.
Yeah. So I'm just sort of curious. If Buck gave him this problem, what the context was for that.
So it wasn't out of the blue. So in fact, there are prior abstracts in the notices of the American Math Society on the same subject or different variations of the same subject. And, all of these people, when I was a graduate student, you would see these names of people who were like always writing papers about matrices. Morris Newman, Minch, Marcus. And I don't know whether they were contemporaries of Sinkhorn or from an older generation than Sinkhorn, but they have been working on some related things. And for example, the instant that Sinkhorn stated his theorem, two of them, Morris Newman and one of the others, observed that if it follows from Sinkhorn's theorem that if the matrix you start with is symmetric, then you don't have to multiply on the left and the right by different matrices. You can multiply, there's a single matrix X such that XAX is doubly stochastic. So Sinkhorn's theorem was original with Sinkhorn, but that topic was being studied by other people. And in fact, there's strange references. Like if you look at Idel, there are, there was a Russian architect who wrote a paper on this subject 30 years before Sinkhorn. There was someone at the equivalent of IDA, Institute for Defense Analysis, who had a working paper where he proposed this alternate row and column scaling algorithm, but didn't even claim to give a proof that it might converge. He just thought this was like a useful way to get in some approximation without any justification that what you got might be whatever it was. So there is a long prehistory of this in various fields. Like architecture, who would think? I have no idea, but yeah. But I will say,
Mel, I have a naive question. This topic obviously has attracted a lot of attention. Is it known what kind of a spectral properties these matrices have and how they behave when you apply these iterations or transformations?
So I don't know. I know that in Idle's survey, which is called a review of matrix scaling and Sinkhorn's normal form, a large part of his paper is on sort of nonlinear Perron-Frobenius theory. But I mean, when I spoke about this once, David Shrunowski observed that in numerical analysis, if you have to solve a system of linear equations, you get a better solution if you start off by scaling the matrix. So it's something close to doubly stochastic. And then when you apply your computer algorithms for finding numerical solutions to a system, you get more reliable solutions or solutions with better errors. So there is a large part of this subject seems to be done by people in numerical analysis. But again, that's so far from anything that I know. And then we have a colleague at City College named Leonid Gurvitz, who is interested in, he's in computer science. He's been working recently with Avi Wigner. Before that, I think he was at Los Alamos. But somehow there's like an analog of this, which is used in quantum computing. And Gurvitz has his sort of like, because I have no idea what it is, I'll just say his quantum computing generalization of Sinkhorns theorem, which people refer to with a lot of respect. But I don't know what, I looked at his paper, but I don't know the language, so I can't say anything about it. Yeah, this is from Idle's survey. When was interest sparked in this alternate normalization, alternate scaling method? The earliest claimed appearance dates back to the 1930s and Kruthoff's use of the method in telephone forecasting. At a similar time, the Soviet architect Shilikovsky considered the method. Sinkhorn claims when he started to evaluate the method, it had already been proposed and in use. His example is an unpublished report by Welsh, who was at IDA. They also acknowledge work of Deming and Stefan in transportation science. So in applied mathematics, which is as remote from me as classical Chinese literature, people have been using this method because it worked, I guess. And it helped them solve, at least numerically, some problems. But yeah. So I'm still, so this first paper of Sinkhorn, I've read extremely carefully. I have to confess, I think when I spoke about this 4 years ago, I made the normal assumption that if I don't understand something in the paper, it's correct, I just don't understand it. But when I finally worked through this first paper, which is the fundamental one, and understood it, I understood that what he proved was something valuable, but not what he claimed. Then Menon, using this Brouwer's fixed point theorem in a very beautiful way, gave a perfect proof, or sorry, that sounds like Trump, gave a correct proof of Sinkhorn's first theorem, and subsequently, but then there is, Russell would ask, what happens if your matrix is not positive, it contains some zeros? There's a whole theory about that. One knows exactly when a non-negative matrix can be converted into or transformed into a doubly stochastic matrix by this kind of method. But and Sinkhorn and Knopp. For some reason, the tradition in mathematics is on jointly authored papers, you always put the authors in alphabetical order. But for some reason in this basic paper of Sinkhorn and Knopp, it's published on Sinkhorn Knopp is not in alphabetical order. I only knew of one paper before that was like that. And that was in Selberg's one joint paper, which was Selberg and Chowla. And since for those of us who knew Chowla, who was the world's most self-effacing mathematician, I'm sure he insisted that Selberg had to come first because Selberg was great and he was the lowly Chowla. But anyway, such is the curiosity of these things. Okay, I apologize for the incoherence of my talk and the fact that I couldn't get my screen share to work properly, but at some point, as I always say, I might actually write this down and put it on archive or somewhere. So the things that I claim to have proved are actually proven and the proofs are written down. And next week, the talk we've all been waiting for, Russell Handel and his co-author. Be there or be square.
All right.
Great talk.
Yeah, very good.
Very good. Okay. All right. Thanks. Okay.
Be well,
Bye,
all.
guys.
See you next week.
Thanks for the plug.
Sure.
Emily and I are going over a mock run tomorrow, so we won't have any problems.
I hope so. I don't know to what extent it's my computer that somehow is at fault, but all right. Anyway, see you all next week, guys.